Hello again, everyone. So for the second talk of the day, we have Professor Srikant from UIUC, who's going to build on the first talk on MDPs and talk more about reinforcement learning.
Thank you. I'd like to thank Wayna for a great introduction. So Wayna talked about Markov decision processes and how to obtain an optimal policy if you're given the probability transition matrix. So the problem I'm going to talk about is typically what's called reinforcement learning, where you don't know the probability transition matrix. So in particular, I'm going to first look at the simplest reinforcement learning problem, which is where you're given a policy pi. So pi is a policy which specifies the probability with which you take action A when you're in state S. Okay, and associated with this policy, there's something called a Q function, which basically says that if I'm in state S and take action A at this point, and from the next step onwards, I'm using policy pi, then what is the value function? So this is also, it's either called the Q function or the state action value function, and V is just the state value function. Okay, so my goal is to estimate this Q function without knowing the probability transition matrix. So if the probability transition matrix is known, as Wayna pointed out, you can think of this as some operator. Q pi is some operator times Q pi. So I'm abusing notation and using T pi also for the Q function operator. She used it for the value function operator. And T pi is a contraction mapping. So therefore, you can just iteratively start from some any Q and then substitute back to get the true Q function. So what I am going to do is, what happens if this is unknown? Okay, the problem clear? So we're trying to estimate the Q function for a fixed policy when the probability transition matrix is unknown. And as I'll demonstrate later on, this fixed policy idea sort of pervades a lot of reinforcement learning. When we try to find the optimal policy, the algorithms look similar, whether you use value iteration-based algorithms or policy iteration-based algorithms for reinforcement learning. All of them are built on the basic idea that I'm going to mention here. Okay. For now, I'm going to assume that we are going to estimate the entire Q function for every state action pair. So the number of states and number of actions could be very, very large, in which case this won't be feasible. So you use something called function approximation in that setting. And I will talk about function approximation later on. So right now, I'm going to consider what's called the tabular case. So where you try to estimate the Q function for every value of S and A, and that's called tabular learning. So I'm going to stick with tabular learning for right now. Okay. Okay, so what is the algorithm? So first of all, let me specify what the data is. So the data is run the policy pi, and then you observe the state and actions. Okay. And you may not even know what the policy pi is. I mean, like if you think of how Tesla, for example, gathers data, you just drive it around in some city, and then you see all the states and actions. Okay. So under some policy pi, we're observing the states and actions. So S0 is the initial state, A0 is the initial action, and then it makes the Markov decision process transition to an S1, and then you take a new action A1 and so on. And so you have T steps of data, data from T time steps. And the goal is to learn Q pi from this. Okay, is clear? So what is the algorithm? The algorithm is this, and I'll explain what the motivation for it is. So if you observe at state K, at time K, let's say the state action you observe is S and A, and at the next time step, you observe S prime and A prime, let's say. Then what you do is you update the Q function, the estimate of the Q function. This Q is going to be the estimate of Q pi. Okay, so you update it in the following manner. So the previous estimate that you had plus, oh, by the way, for simplicity, I'm going to assume R is deterministic. Given SNA, R is not random, but you can also allow randomness here. But for simplicity of notation and so on, I just assume that this is deterministic. So for the state that I observe, I update the Q function. And for all other state and action pairs, I'm not updating the Q function. Is that clear? And what is the rationale behind this algorithm? So basically, you're changing the Q function slowly. Your estimate of the Q function very slowly. So epsilon k should be thought of as a small number, right? It could potentially depend on time. You could have time varying epsilons, or you could use fixed epsilon. So the idea is that you put a lot of weight on the current estimate. And what you do here is that your estimate of the Q function when the probability distribution is unknown is just simply R plus gamma times Q. Okay. So, but I put a small weight on that because that's a random quantity. Okay. And I don't believe in it as much. So therefore, it is just a convex combination of the two. And it's actually the same thing as the law of large numbers, or how to estimate the mean. So if you have t realizations of a random variable, independent realizations of a random variable, this can be written, of course, as and which can further be written as right? So this is your previous estimate after t minus 1 observations, and you put a small weight on it, and then put a large weight on it, and put a small weight on your new estimate. Okay, so this way of estimating random quantities is called stochastic approximation. This is a very old history. I think Robbins was mentioned yesterday in the context of multi-arm bandits. It's the same Robbins who also came up with stochastic approximation, Robbins and Monroe.
If you put 1 over t, you put 1 over square root of t or 1 over log t, this will not work, right?
No, it may not work. Correct.
So don't you have to choose a particular epsilon k?
Correct. Correct. There will be conditions on epsilon k for which you have convergence. Yeah. But often people are not interested necessarily in convergence. You're going to stop it after a finite amount of time. So there are different types of step sizes that are analyzed. So I might, yeah. So let's look at let's not worry about the conditions on epsilon k, but you can think of it as 1 over k, for example, for right now. Okay, so this is the stochastic approximation algorithm for estimating the Q function. Okay. But I want to say something which is peculiar here. This is what might be called an asynchronous algorithm because you're only updating one element of the Q vector. The Q vector is a vector of dimension S times A, where S is the size of the state space and A is the size of the action space, right? But at each time, I'm only updating one element of the Q vector. Okay, and so it's not so that's why it's slightly harder to analyze than this, right? Here we just have one parameter you're trying to estimate. Here I have a vector I'm trying to estimate, and I'm estimating one element of I'm updating one element of the vector each time. Okay, so we still have to show the same ideas like law of large numbers hold here as well. Yeah.
How do we initialize Q0?
It doesn't matter. You can initialize to be anything. Yeah, but we should probably write that. Some Q0. Yeah. Okay. probably more convenient. Or should I just stick to the middle? Maybe I'll try to stick to the middle as much as possible. Sorry? Oh, you can still see it there? Okay. As long as it what?
There's a lower bound.
Oh, yeah, there's a lower bound here. That's true. So QK plus 1 SA can be written as QK SA minus epsilon K indicator SK AK equal to SA QK SA minus RSA minus indicator SK plus 1 AK plus 1 S prime A prime Q. Okay, so I'm basically just only updating the parts of the Q function that the states and actions that I observe. Okay, so if I define in vector notation, the whole thing can be written more compactly, and you'll start seeing why it looks like the Bellman equation for a fixed policy in a second. Suppose I take the entire vector Q, okay, and I can write it as QK plus 1 is QK minus epsilon times D0K QK minus R times gamma times D1K, where D0 and D1 are SA by SA matrices. Okay, so instead of writing this for one element at a time, I'm trying to write it for all elements at a time. And so what I have to do here is that this D0K will have zeros along the diagonal except a 1 at one point, which is this indicator function. Okay, and similarly D1. Okay, D1 will have a 1 in the place where S0 SK AK is SA and SK plus 1 AK plus 1 is S prime A prime.
So D doesn't stand for diagonal.
Sorry?
D does not stand for diagonal.
Yeah, probably. Yeah, if you want, I can use E here. Yeah, D is diagonal. This D0 is diagonal. D1 is not. Correct. You're right. Good point. The main reason I wrote it like this is that if you look at this, this looks a lot like the Bellman equation. Okay, if this would be a diagonal matrix consisting of the stationary probabilities of SA under policy pi. So this is an indicator function right now, but if you look at this in expected value in steady state. Okay, if you assume that the system is stationary, which it is not, but if it was stationary, then this is just simply would be just the expected value of the indicator function SK AK equal to SA, which is just simply the probability of seeing SA. Okay, so I'm going to indicate this diagonal matrix by d pi. Okay, this would be the expected value of this, and expected value of D0K, D1K would be, so this indicator indicates where you are in the at state k, and this indicator at time k, and this indicates where you are in time k plus 1, right? So this will be just simply the stationary probability multiplied by the probability transition matrix. Okay. So if I substitute these stationary probabilities there, then this equation is going to look very familiar to you after Wayna's talk. So if I substitute the stationary probabilities there, which of course is not quite right, but I'm going to do it anyway. Sorry, this should be epsilon k generally, but so I replace these two by their stationary expectations, of course, which is not correct. And so I can think of this as this plus nk, where nk is the difference. Epsilon here. The nk is the difference between the true thing here and the stationary probability. Okay.
Your gammas and R's are looking a little.
Oh yeah. Sorry, this should be R, and I try to write gamma like this. Sorry, thank you. Yeah, I have that problem with gammas and R's. So this is equivalently so this whole algorithm can be thought of as another way of solving the fixed point equation. Fixed point equation normally is solved by you start with the q, find a new q by applying by running it through t pi and keep doing this. The fixed point equation just involves these two. But since I don't know the probability distribution, I do this. Okay, and this algorithm is called temporal difference learning algorithm, or TD learning, because this is called the temporal difference. The difference between the right-hand side and the left-hand side of the Bellman equation, because it's a time varying thing, is called a temporal difference algorithm. So this is the basic algorithm in reinforcement learning, where I'm fixing a policy and I'm trying to evaluate the Q function or the value function associated with it. In this particular case, I'm writing it for Q function. You can also write the similar thing, a similar thing for the value function B. Okay. So our goal is to show that this algorithm converges. Okay, and it's vaguely motivated by essentially how to estimate the mean of a random variable. Okay, so the most natural thing to do would be to study how this quantity evolves. Right? We want to show that qk converges to q pi. Okay, so anybody who has taken a course in control theory, for example, this would be called a Lyapunov function. Right? You study the drift of this Lyapunov function and try to show that it goes to 0 or it goes to some small value, whatever, depending on what step sizes you choose. Questions? Okay, yeah.
Basically, why we don't first estimate the transition matrix and use that, but why we are using this approach?
Good question. So later on, we will, in practice, you may not even have a model in the sense you may not even know how many states there are in your system. So when you do use neural networks and stuff like that, which I'm not going to talk about, I'll try to approximate. In general, people approximate the Q function using a neural network, for example, and just you give a state and action as input, it just spits out the Q value, and it doesn't need to know what even the states and actions are ahead of time. Whereas to estimate the probability transition matrix, you need to know these are the states in the system, these are the actions in the system. So I need to estimate the probability transition matrix. And I don't know if this is another reason or not, but that's a SA square number of elements. Here we're just estimating SA elements. So Q vector is a SA is a vector of dimension S times A, whereas the probability transition matrix is the square of that. Yeah, for each, if I'm thinking of the P pi, yeah.
So, but if I put those aside and I said, oh, I'm just going to estimate probability transition matrix and then use that to estimate Q, is it like inferior? Is it superior?
Well, I mean, it's not feasible is what I'm trying to say. It's feasible for small problems.
Right.
For large problems, what we'll do is we won't estimate the Q function like this. We would probably, I mean, later I'll say that we're going to try to assume that Q has some functional form like this. And try to estimate this theta. So phi would be a set of feature vectors associated with each state in action. For example, if you're playing Tetris, right? I assume most of you know what Tetris is. You have these blocks that fall and then you try to knock off things at the bottom. And the state is very complicated because, I mean, the actual shape and where the holes are and so on is a state, but a feature vector for this is kind of easy. You can just see write down the length of each column and where the holes are, and that's a much smaller feature space. And then you try to find a Q function, like, so you assume the features are known associated with each state, and theta typically will be of some dimension where D is much, much smaller than SA.
Would you do the same with the policies, and your policy would become a kernel?
Yes.
Of the feature
Yeah,
space?
so you can do this for policies as well. Yeah.
Right,
So
no, but you could also do it for transition probability.
for transition probabilities,
There would be a probability kernel on your feature space, which is
Possibly.
also a nice function.
possibly, but for whatever reason that is not the approach that's taken. I don't know why that's why that is infeasible, but typically people try to directly estimate the value function, because once you estimate this, but I think the structure in the problem, if you know something about the problem, then I think exactly what you said should be done. You should take the structure. So this is all assuming that there is no structure in the problem, which is not a very good idea if you, for example, if you have a linear quadratic Gaussian problem or something like that, where you know that the problem has some structure, then of course you should take the structure into account when you solve the problem. Yeah.
I think this is maybe just like a small notation misunderstanding.
Yeah.
The indicator on the like very right-hand side.
Right. Yeah, I don't know. I didn't write it carefully. So think of this indicator as the product of these two indicators is just
So, but like, I guess, where do S prime and A prime coming from? Are we just
that is
summing
the
over?
next state. That is the next
Okay,
state.
okay, but
Yeah.
okay. So, but like,
Yeah.
Are we summing over all S prime and A prime such that we only end up taking one of them?
Yeah.
Cool.
Yeah. Sorry?
Epsilon K, N K.
So NK is the difference between this quantity and the true one. So this here I've taken remove D0 and D1 and replace them with the stationary expectations, right? But really it is this difference I'm just calling noise. Calling it NK. Okay. Okay, so I want to analyze that equation. So first I'm going to do a noise-free analysis. I'm going to pretend that there is no noise in the system. And typically this is the trajectory of analysis, which is basically you write it in this form, where your QK minus something that's completely well known, and then add everything that you don't know as noise, and then ignore the noise, try to analyze the system, and then try to understand what happens to the system with the noise. Okay, this is sort of the summary of everything in stochastic approximation. Yeah.
So another notational clarification question. So D0 and D1 are 0-1 matrices that correspond to the actual realization.
Correct.
And this equation is the
Correct,
expectation.
Exactly. This is expectation, and these are the actual realizations. Sorry, the difference between the actual realization and this is what I call NK. Okay. Okay. So let's look at the noise-free model.
And then I still have a question there. So your Q, so the D pi times P pi is the calculation.
Maybe I could have just written SK plus 1, AK plus 1 here without putting indicators. What whatever you observed here.
No, but it's I still have the same question because you take the.
So the expected value of this quantity would be P pi.
You write it as expect. So you write the expectation of a product at. It's not quite the product of expectation.
It's not if you condition on it. So this is a stationary distribution, and then this is
the conditional expectation.
Yeah. Yeah.
Is this K plus 1 or just K, like the index?
This index should be K, correct?
This NK is 0. So it's a random matrix.
NK is a random vector whose expectation is 0, conditioned on Q in steady state. So it's not 0 at any time, but it's 0 in steady state, and that's one of the challenges that we have to overcome. Okay, so expected value of NK conditioned on QK equal to 0 if you assume in the stationary region. Okay. But it's not, and so you have to worry about that. So that's the crux of the argument for the noisy case. But first, let me look at the noise-free model. So basically, I want to understand the evolution of WK, right? I want to see whether QK gets closer and closer to Q pi, right? So I'm going to, so people call this the potential function in computer science literature, the Lyapunov function in control theory literature. So this is, I'm going to do a Taylor series, because it's very easy because I have a quadratic function here. It won't be this easy for all problems, but since I'm starting with a quadratic Lyapunov function, the second derivative becomes the identity matrix. And so this is, you don't have to write it necessarily using Taylor series because the quadratic, you could have just expanded this. But I'm writing it in this particular manner because later we'll see for some other Lyapunov functions, you'll figure out how to do this. Okay. And this is nothing but WK plus QK minus Q pi transpose. What is this quantity in the noise-free case? It is just nothing but epsilon K times d pi, d pi in the middle, times QK minus this. So what I'm going to do now is to write QK as QK minus Q pi plus Q pi minus T pi. The reason I'm writing it like this is I want to write this again in terms of Q pi minus QK. And we know from Weierstrass that Q pi is nothing but T pi Q pi. And so this is nothing but T pi Q pi minus T pi QK, and then I use some contraction property to get rid of the T. Okay. Plus epsilon K square, I'm going to put a M here. Plus, it's not very difficult to show that the TD learning algorithm is bounded. Okay, so here this is due to the fact that norm of QK is bounded by some property. I'm not going to prove that here, but that's a very straightforward thing to prove because we are taking convex combinations of some initial value plus something bounded, so it will always remain bounded. Okay. So this is, but actually you can do a more finer analysis for the deterministic case, for the noise-free case, and get a better result than what I'm going to show here. But what I'm going to show here is what will carry over for the noisy case. Okay, so what do I do now? Everybody see this? It's too low. Is it okay? Okay. So WQK minus epsilon K times the first part is nothing but QK minus Q pi square, except it's a weighted norm. So it's QK minus Q pi transpose D pi times QK minus Q pi. So it's a weighted true norm weighted by this matrix D pi. Okay, that's the first term here. Okay, understand that. And what do I do about the second term? So that is plus epsilon K 2 QK minus Q pi 2 D pi multiplied by Q pi minus Q pi QK. So what have I done here for the second term? What have I used here? So I have QK minus Q pi transpose D pi times Q pi minus, so it was an inner product, right? So weighted inner product. And what I'm doing here is the Cauchy-Schwarz inequality. So I'm using the Cauchy-Schwarz inequality to write the inner product in terms of the norm, in terms of two norms, right? So again, after I use the contraction property here, I will get QK minus Q pi squared, okay, plus this M epsilon squared. Okay, it's clear, it's not clear. I'll explain it again. So the first term is just QK minus Q pi squared weighted by D pi. The second term is QK minus Q pi transpose this thing with this weight. And so under this weighted inner product, I just write the Cauchy-Schwarz inequality. Cauchy-Schwarz, yeah.
So what is the M here? It depends somehow on the size of D pi.
Right, so the M is just simply, well, all I'm saying is that this is a actually bounded iteration. So QK minus Q pi will be bounded always. So the square of that will be some quantity that's like epsilon squared times some constant here. You can prove that this whole iteration is bounded as a function of the initial condition. Yeah. So this needs a proof that norm of QK is bounded, but it's very straightforward, so I'm not doing that. Yeah.
For that epsilon case, the epsilon case would be 1, would it still be bounded, or do you need the summer or something?
Yeah. You will for a sufficiently small epsilon k has to have some conditions as to which it will. Yeah, I'll get to it in a second, but yeah, epsilon k has to be some. I have to have some conditions for which. Let's assume that mostly I'll consider this case. But it will also work for other cases like. In those cases, it still show. Yeah.
I have a question on the first.
By the way, this is motivated by the fact that in the law of large numbers, you have 1 over 2. Yeah.
First line. There's a gradient of value.
Right. Which is QK minus Q pi.
Based on this.
Yes.
Where does D come from?
D comes from this equation QK minus Q epsilon times D.
I see.
Okay. Okay, so now this is further less than or equal to WQK, okay, minus epsilon K QK minus Q pi, not quite the 2 norm, but the weighted 2 norm, plus epsilon K gamma QK minus Q pi. And this is due to the fact that Q pi minus P pi Q pi QK, sorry, 2 d pi norm, the same as P pi Q pi. First part, I'm using the fact that Q pi is just nothing but P pi Q pi minus P pi QK with the 2 d pi norm. And this has a contraction property, which Rayner did not prove, but it also holds. So Rayner proved that this is a contraction in the infinity norm. It also turns out that for a fixed policy, this is not true for the optimal Bellman operator, but the Bellman operator associated with the fixed policy is also a contraction in the weighted, if the norm is weighted by the stationary distribution. By the way, throughout, I'm assuming that the policy is such that pi, the stationary probability being in any state is positive. Okay, non-zero. So this is less than Q pi minus QK plus this M. Yes.
Inequality, is it specific to the stationary distribution or any,
Yes.
any distribution?
So it's specific to the, you can only weight this by the stationary distribution. Yeah. I don't have a good intuition as to why that's true. So I think basically if you write this out to prove this, it's very straightforward. You just use the Cauchy-Schwarz inequality at one point and use, well, actually, basically T pi has a P pi, and it has to, you have to multiply by d pi multiplied by P pi. It's like, again, can be written in terms of d pi. That's why. Yeah, so you need, because the stationary distribution, you have to multiply, there's a point where you have to multiply with the probability transition matrix, and then you get the stationary distribution again, otherwise you won't, this won't work. Okay, so now we have business. So WQK plus 1 is less than or equal to WQK times 1 minus epsilon K times 1 minus gamma times so notice that this is a weighted 2 norm, whereas W is the unweighted 2 norm. So therefore, to get rid of it, I have to, because there's a minus sign here, I have to, I use the smallest value, the diagonal of D. So I'm just calling that D. So this is it. I mean, if epsilon K is constant, let's take that case. Epsilon K is constant. Of course, this is a stable recursion. If epsilon is sufficiently small, it's less than 1 over 1 minus gamma times d min. Okay, in which case you can show that WQK converges and it will be a form of epsilon. Okay. So if epsilon K is epsilon and small enough, then in the limit, I should put it so because I don't know if it converts for sure. Something like n, some of that constant times so small. So if you use diminishing step sizes satisfying those conditions, then you can show that it actually goes to 0. Okay, actually, in this particular case, in the deterministic case, you can actually show that this goes to 0 even for the fixed epsilon. But because I did this crude approximation here, you can't see that. But you can show it in the deterministic case. But this is more useful in the stochastic case. Yes.
Sorry, maybe you said this, but can you can you explain again where d min comes from? And
So it is just basically I'm replacing this quantity.
Yeah.
I'm just saying that Q1 minus Q2.
right, W is an unweighted 2 norm.
Correct.
Right. Okay.
Yeah, so this is
So this is a weighted 2 norm.
Sorry, that's greater than because it's a minus sign. Correct. Yeah.
We may not exactly know that the distribution has supported. So we need to somehow design.
So you have to. So in reinforcement learning, you need exploration.
Right.
Okay, like in chip crosstalk, I mean, you need exploration for multi-arm bandits. So the policies you try are typically randomized policies which allow you to explore every state action space.
We want to design policies to guarantee correct.
Exactly. So I'm assuming there's a policy that is randomized and will visit all state action pairs. Right. More cleaner connection between chip crosstalk and reinforcement learning will be in Sean's talk later this afternoon.
But do you need that to estimate, just to estimate Q? You might need that to optimize.
Correct. Yeah. You need
policy, but do you need that?
Yeah, if you're interested in just estimating the value function associated with it, you don't need that. I mean, for Q pi, you do. If you want to estimate Q pi for every state action pair, of course you need it. It depends on what you. So if you're interested in estimating V pi of S, you just need to make sure that every state is visited. If you're interested in Q pi of S comma A for every S and A, okay. I guess if some states and actions are not visited, maybe you don't require it, but I'm not sure what will happen to this D here. Because of this norms not matching, it might be a problem. But anyway, this is just one piece of trying to learn the optimal policy. And when you're trying to learn the optimal policy, you need to explore every essay. And for that reason, I'm just considering those kind of policies. Okay. Okay, so now let me look at the noisy case.
So your Laplace function doesn't really go to 0. So
as I said, if I did a more careful analysis, actually it will go to 0 in this case, but I didn't. Yeah, but if you choose, even in this lazy analysis, you can make it go to 0. Epsilon k always goes to 0. Yeah.
Quick question. So this is more or less just like a first order method for finding the fixed point of a contraction.
Correct. Essentially that. So it's in the second part, you have to worry about the noise.
Right.
And there we'll figure out how to.
Is there any more modern treatment people think about this as some sort of first order method known the southern point optimization? Like momentum method.
Even finite time bounds for this are very new, actually only in 2019. So typically what people used to do is that they used to write this in terms of the expected value of this conditioned on the past is less than or equal to this, and then they would use the super martingale convergence theorem to show asymptotic stability. So in this code 29, so much of my presentation is based on this. It's a simplified presentation. This is based on the code 2019 paper. As you will see, this gets more and more complicated as you when you try to learn the optimal Q function, or if you're trying to do policy iteration or value iteration based methods to compute the optimal function. Yeah, this is very basic. These ideas were also used in the original, I should say, Sinclair and Mandroy. So asymptotic convergence. In 1998, meaning as k goes to infinity, instead of being able to provide finite time bounds, they would just essentially then appeal to the super martingale convergence theorem to show asymptotic convergence. So how do we deal with noise? And this is Markovian noise. If it's IID noise, it'll be very simple. But we have Markovian noise. Right? So the Markovian noise NK is the Markovian case. I mean, so in the noisy case, we have this NK. So the main difficulty is figuring out how to deal with this. Okay, because NK is not an IID quantity. It's a very complicated quantity, but what we do know about this is that expected value of D0 is d pi. I mean, in steady state, an expected value of D0 times D1 is this. Stationary expectations have this. Yeah.
The other way around, the thing you've written is NK, because I thought that the NK was the difference between the
right.
The
but I put a
binary
plus here, right? Because there's a minus here.
Oh, I see. Okay, got it. Got it.
Okay. Okay. So what do we do about this? Okay. So now so what will happen is if I do W2K plus 1 minus WQK, okay, so this will have the same terms as before. Plus the gradient of WQK times epsilon NK. And then it'll also appear in the quadratic term, but that will still be order epsilon K squared. So I'm going to absorb it here. So I'm just redefining the M that I had here and just calling it MK epsilon squared. So this is the term we have to worry about. Okay. So if we can show that this quantity is order epsilon, okay, actually, yeah, this quantity is order epsilon squared in some sense, then we'll have a similar result like this. Okay, but of course, it's not going to be true in a deterministic sense. So it can only be true in some stochastic sense, right? So what I'm going to do is, okay, so I think most of you probably know this concept. So if I call, let me just write it somewhere. Okay, so we have to somehow exploit the property that in stationarity, the expected value of D0 is d pi. Okay, but that's not, that can't be, but when you're trying to do a finite time analysis like this, you can't rely on that. So what I'm going to do is I'm going to say if you run the system for sufficiently long period of time, at least for tau epsilon amount of time, okay, then the expected value of D0 is going to be epsilon close to d pi in the total variation distance. So if you just, because it's only diagonal, so you're comparing two probability distributions, And then so therefore in the total variation distance, so this, if you don't know what this is, just think of it as tau epsilon is amount of time that it takes for the distribution to get close to the stationary distribution. That's what's called an
expectation. So I said this solution that E of P0 of K seems to be.
Yeah, but that's so the diagonal element will be a bunch of expectations, each of them of an indicator function. So there's all the probabilities in interpret them as probabilities.
I see. So I think of it actually your space in which you take the variation is just a vector space.
The diagonal elements. Yes. Yeah.
That's not one.
Yes, because it's only one of them will be 1 and the rest of them will be 0. Yeah, d pi is the stationary distribution by definition. Yeah. So the diagonal element of d pi. Yeah.
Why couldn't I just take the expectation condition on QK and then say you have a Martingale sequence that is
no.
Like the inequality that you have, the difference between W Q K plus 1 minus W Q K. After you add the noise back, take the expectation condition on QK, then the noise cancel.
No, but this won't be. If you condition on QK, DK, D1 may not be close to D pi. If you condition on QK, D0 will not be close to D pi because of the one step difference. So, but you've gotten the idea basically. So what you have to do is.
So here, total variation is just a 1.
Yeah, but I think his question is that why not condition this on.
So if you condition the stationary distribution, then they're going to be equal. Right now, you're conditioning something that in TV distance is close to this.
Yeah, I'm going to condition on the history up to tau epsilon time units in the past.
So you can couple.
Yes. Yeah. So if you put condition on tau epsilon time in the past, then at the current time will be close to the stationary distribution. Okay. So this requires some algebra here. But I'll try to outline. So nk consists of all of these terms. Let me take one of the terms in nk. Nk consists of many nk is like this, right? So if I look at this, so it's a difference between these two things. I'm just looking at the difference between the first terms here. Okay, you have the same analysis can be carried out for other terms. So when I look at gradient of wk transpose nk with an epsilon in front, you'll get epsilon qk minus q pi transpose d pi minus q0 qk d0 qk, which is approximately epsilon times qk minus tau minus q pi d pi minus d0. I'm hand waving writing everything here. I'm going to replace qk by qk minus tau, but qk minus tau and qk differ. It's tau over, you're summing up over k. You're looking at the difference between qk and qk minus tau. And since each time you're adding a bounded quantity, the amount that will be different by is epsilon times tau. Let me just consider the fixed epsilon because it's okay. So you have an extra term like this, and then this. Now these two are order epsilon close if you condition on hk minus epsilon. History up to not at the current time, but you condition on the past to tau epsilon. Then d pi will be close to d expected value of d0 when you condition on h k minus tau will be close to d pi. And so this whole thing can be shown to be order epsilon square. Conditioned on this. So basically what I'm saying here is, I mean, this is a lot of stuff here, but this part is the computations are somewhat cumbersome, but what you can show is W2 conditioned on tau will be something like I guess that's not quite right. We get exactly the same thing we had. So first condition on hk minus tau, and then take expectations again to uncondition it. And then after uncondition it, you'll get it. So now it becomes essentially like a deterministic problem. For sufficiently small epsilon, it'll converge. Yeah.
When you hand wave to go from k to k minus tau, is that what was the big intuition behind the hand wave?
Because this is so each time you're adding this much. So in tau time units.
Oh, there's a times tau. I
Yeah.
didn't see that. Okay, cool. Thanks.
Sorry, this should be multiplied by epsilon tau. And this, for those of you who know about mixing time, will be of the order of log of 1 over epsilon. So it's not quite epsilon squared anymore, but it's epsilon squared times log of 1 over epsilon. Okay.
Assuming you need more on the transition.
Assuming the what?
So you need the.
So I'm assuming the transition probability matrix for this policy is irreducible and aperiodic. Yeah. So it has a stationary distribution, it has a mixing time, it has everything, the nice things that you need. Yeah. So that's why a good exploratory policy is needed here. I think the hour is up. So this is the basic stuff. So this is TD learning. And so we will build upon this ideas to figure out what the optimal policy is. Okay. That'll be the second part of it. Any other questions? Yeah.
I'm wondering in practice, since you said there's very, very large state spaces and you need to make sure that you explore the entire thing. How does that work? How do you kind of make sure that your policy will...
Well, I mean, in real life, probably all you just get is a trace and you can't, you hope that you've explored everything. But if you have the ability to design a policy, you probably do a randomized policy. And the policy randomized, you just hope that you use a randomized policy that visits every action, that takes every action in each state, it's a non-zero probability, then that hopefully that it can use a probability transfer matrix that has the right property. Yeah, well, I mean, the whole thing is a hope because it may not even be a Markov.
Yeah.
What we have, it may not even be an MDP, but it works. Yeah. So if you assume it's an MDP, and if you use an exploratory policy, in many cases people have made things like inverted pendulum stand up with this and so on. So yeah.
So you mentioned before that you might think of it that there's some feature vector in the background. So is there some way to make this rigorous in the non-parametric setting?
So this you're talking about? Yeah, so that's what I'm going to talk about next. Yeah, I'm going to talk about this next. Yeah.
Is it possible to use this same framework to derive some bound in terms of infinity norm instead of two norm?
Yes, there is some recent work by Martin Wainwright and Ashwin Pananjari on doing this, but I haven't looked at it carefully. So, but there is work by Oh, I must also say that very closely related to our paper, and done a little bit before our paper is actually this. They assume a projection step, which we don't, and that's the main difference. So I would recommend reading that paper as well. And yeah. Oh, yeah. Yeah.
Maybe this is a stupid question, but what are the conclusions we can get from this last equation?
Oh, so you can show that. So from this, you can show that this limit is order epsilon. If you use fixed epsilon, if you use epsilons that satisfy these kind of conditions, you can actually show that it goes to 0.
But what about like sample complexity?
Sample complexity. Now it will. So this will be some constant times. You can write a. So from this, you can conclude that this is less than or equal to some.
The rho is
Rho is some number less than 1 that depends on the choice of epsilon. If you use a fixed epsilon.
But I have to choose epsilon.
Or you can use this. If you use epsilon equals 1 over k, for example, then instead of this, you can prove a result of this form. So W0, WQ0 divided by T. So one nasty thing here is that this depends on d min. Right? D min could be very, very small, right? So it's exponentially converging, but then it's converging very, very slowly. But you can get a 1 over t result without actually any dependence on d min. Sort of like an optimization, right? I mean, you either get exponential convergence for fixed step size, or if you use 1 over t step size, then you get 1 over t convergence.
So I imagine this will become important.
Yes.
You may not want to explore.
Yes. So when you're using this inside another algorithm to find the optimal policy, then yes, all of this you need. It's somewhere between exponential but very, very slowly, or 1 over t without depending on anything.
So I mean, this is getting the bounds on the 2 norm over the entire Q matrix.
Right.
But suppose at the end of the day, I just want to know the argmax range.
Argmax here, right?
I'm saying in general, if I don't really care about the Q matrix, I just care about the largest value in state.
But not here, not here. This is just evaluating for a fixed. I'll get to it. Exactly. Yeah.
So general sample complexity somewhere in y was the variance, right?
Yes. So this is sort of, I mean, this is sort of like a variance term, right? Because this is a quadratic term, and this is
Not obvious to me how for constant step size you are, like, wouldn't the sums of variances go to infinity or something like that?
so you can prove this, that the limit of this is order epsilon. And this
But
is
that's an
like,
expectation.
this is like a variance, right? This is like q k minus q bar.
Well, even for constant step size, the variance goes to 0.
Then go to 0.
I guess what you're saying is if someone fixes capital T, like they tell you the finite time, you can choose a smaller number.
Yeah.
Else you should use something.
Yeah, exactly. Exactly. But sort of even then, because epsilon depends on d. Yeah. I mean, it's like an optimization where epsilon is chosen as less than 1 over L or whatever. So if you know the function is L, then you can do it. If not, you can't. Yeah. Smoothness constant. Okay, should we take a break and then come back?